All right, so in 10.1, we did some vocab, right? And then we talked about two theorems in particular. One that says that if a line is tangent to a circle and it intersects the radius, it hits it at a right angle, so be perpendicular. And the second, which is this one, that ice cream cone shape, that says that if two segments that are tangent to the circle have the same end point, then they are congruent. So these two would be congruent. I would set 3x minus 1 equal to 2x plus 11. Subtract the 2x. X minus 1 equals 11. Add the 1. And x equals 12. Okay. On your quiz, you will see stuff like in the homework where you had to set them equal to each other, factor, that kind of stuff. But you're going to definitely see this theorem. Yes, sir?
Will the ice cream cone be used a lot in the quiz?
I wouldn't say a lot, but there's one or two questions on it.
Not as easy as the ice cream cone?
They're like more like a factor, like where you have to set it equal to each other and factor it. Some of it is easy though, yes. So 10.2 is called finding arcs and measures. Okay, we're diving deeper into circles. The whole chapter is circles, but and other shapes built into circles as well. But we're going to talk a little bit more about the circles today and the arcs on those circles. So a central angle, which is a new vocabulary terminology, says, vocab term, an angle whose vertex is the center of the circle.
I can't find the template.
So a central angle has vertex at center, and then the sides of that angle are also radii. This is called a central angle. So in this case, angle ABC is a central angle. The vertex is on the circle. On the center. An arc is the broken part of the circle. So it's like the crust of the pie. Just that outer ring. So if you had your circle.
Is it only the slice though?
Not the slice, the outer crust of it.
Crust of the slice.
Yes. So if
the crust of the whole pie?
this little red, that's called the arc, okay? But there are three different types of arcs. A minor arc, which is one that is less than half the circle.
Less than 180 degrees.
Correct.
So like acute?
No, minor, because acute would be less than 90.
Yeah.
The semicircle is exactly half the circle, so 180 degrees. And the major arc is bigger than half the circle, so it's bigger than 180. So less than 180 is minor, equal to 180 is the semicircle, and greater than 180 is the minor arc. So you're going to classify these. The whole circle would be 360. You're welcome. All right. So in this diagram, if you are given that DC is the diameter, then it cuts this circle. As soon as you draw a diameter, it cuts it into two semicircles, okay? If you then divide that semicircle like this is done with another radius, then it cuts that semicircle into two arcs, and those would both be minor arcs. So arc AC and arc AD would both be minor arcs because they're less than half.
Who made these notes? They made a mistake.
Where?
That arc AC and AD.
Oh, well, it's just an example of one. It's not necessarily a mistake. Arc DAC all the way around halfway would be your semicircle. And then arc ADC, and it has to go in that order. So from arc A to D to C would be a major arc because it's bigger than half. So part of the questions are going to literally ask you to name an arc, to name a major arc, a minor arc, something like that. You'd want to be able to name it from a diagram, or if you were given the diagram, you'd want to be able to identify, you'd want to be able to classify it.
Can there be more than one major arc?
Sure.
No?
Yeah, because ACD is also a major arc, right? ACD is also a major arc. It's bigger than half.
So they can overlap.
Sure. All right, the measure of an arc is equal to the measure of the central angle. So whatever angle, it has to be the central angle, so the actual vertex has to be at the center. Whatever angle is inside the circle at that angle is going to be the same as the measure of the arc. So angle ABC there is 50, which means arc AC would also be 50 degrees. And this is in degrees, not length, so we're talking about degrees. Arc length is something entirely different. The measure of arc CAD would be what? How do you know it's 180? Good. Good. That's the diameter. It's half the circle. It's a semicircle, 180 degrees. And then arc ACD.
That's obviously 230.
It's 230. Why is it 230? This would be 180 plus the 50, 230. Questions on those?
Yeah, I didn't know.
Good.
I should have read the directions because instead I just put minor arc, semicircle.
Okay, well, let's do that. Classify. What is AC?
So AC is minor arc.
Minor.
And
CAD?
is semicircle.
Semicircle.
And the last one's major.
Good. But good tip. Read directions, right? All right, adjacent arcs are arcs that have exactly 1 point in common. So arcs are adjacent, meaning they cannot overlap if they are next to each other. So I can say that ST and TQ are adjacent because they share T. They cannot overlap and they can't be separated out. So you could also say TS and SR are adjacent. I can say SR and RQ are adjacent. And I can say RQ and TQ. Sorry, and QT or TQ are adjacent. So they are next to each other. They share 1 point. They do not overlap. Go. All right, postulate 1.0 or 10.0, just again, number means absolutely nothing. It just means it's the first postulate in chapter 10, okay? The name here is important, and it should seem somewhat familiar because we've had something like this a couple of times. This is called arc addition postulate. So we have done segment addition postulate, and we have done angle addition postulate, which basically says if I take a segment or an angle, break it down into 2 parts, I add it back together, I get the whole. It is the exact same concept, but with arcs. So the measure of an arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. So if I had arc ABC, I went all the way around, ABC, again, the order of the letters is important. If I wanted to find that measure and I knew the smaller 2, I just take AB and add it to BC to get the whole arc. So that is the arc addition postulate. If I wanted to know arc ACB, then I would add together AC and CB. And what should be true about all of the arcs if I added the entire thing up? Good, they should equal 360 every circle. All right, theorem 10.3 is called congruent circles theorem, and it says 2 circles are congruent circles if and if they have the same radius. We talked about this when we did congruent circles in 10.1, okay? But this is what they could look like. You have 2 circles there, and the 2 radii are marked as congruent. It's also just the definition of congruent circles. But this time you're also using it the other way because we say if and only if. So if they have congruent radii, then they are congruent circles, and the reverse of that, if they're congruent circles, then they have congruent radii. Just goes to tell you that all the radii would be congruent. All right, congruent arcs. Think congruent, same, and equal, right? So now we're saying 2 arcs are congruent if and only if they have the same measure, and they are arcs of the same circle or congruent circles. So you can know, I can't say that I have like some teeny tiny Okay. These arcs would not be congruent because those circles are not congruent. They either have to be in the same circle with the same measure or they have to be in congruent circles. So if there was another circle, or if let's just say I go in the same circle, if I went this way and I said 30, then these two arcs are congruent. Or if I had drawn and I know that this is 3 and this is 3, let's say the radius is the same. Now I can say those are congruent. So this would be like FG. I can say FG is congruent to that because those are congruent circles. So they either have to be within the same circle or within congruent circles. This would not be congruent even though the central angle is the same. Questions so far? Yep. Correct. It has to be a congruent circle or it has to be the same circle. I mean, if you think about it, like if you actually took a string, right, and you measured this and you measured this, those are going to be different length string if they're not the same size circle. It should make sense. All right, theorem 10.4 is called congruent central angle theorem. And it says in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding angles are congruent, which is basically what we just drew out. In the last one, I technically probably should have put it on the actual arc itself, okay? If the arcs are congruent and they're in congruent triangles, those are congruent. But also, in this case, if their corresponding angles are congruent, they are also congruent. So if in the same circle, which would be this one, those two are congruent, then these two are congruent, or vice versa. Or if I had another circle that was congruent to this one, so if the radii were both 3, again, let's say, and I had an angle that was a single arc like this single arc, then all 3 of those would be congruent. So they have to be in the same circle or in congruent circles. But if the central angle's congruent, then the arc's congruent. If the arc's congruent, the central angle's congruent. All right, and then theorem 10.5, similar circles theorem, which says all circles are similar, okay? Like our model with our scale factor with a, if there was a small right triangle and a big right triangle and they were similar, all the angles would be the same, all the sides would be proportional. It's kind of like that, except it's a circle. It only has one unit of measurement. Your radii or your diameter is the only thing that you can use. So they are all similar. And two arcs are similar arcs if and only if they have the same measure. This time they don't have to be the same size circle. So if this was 30... and this is 30, but they're not necessarily, well, it's not 30, but get the point. But they're not necessarily the same, they're not congruent circles. These arcs would be similar. Not congruent, but similar. All right, now we do the examples. So example 1, name from this diagram 2 minor arcs, 2 major arcs, 2 semicircles, an acute central angle, and 2 congruent arcs. All right, so I said it before, but I'm going to remind you again. So a minor arc can use 2 letters, but a major arc in a semicircle has to have 3. So give me an example of a minor arc. Go. AR or RA, that would be the same arc. That is a minor arc. What's the other one? CR or RC. Those are both your minor arcs. See what? Yeah, I mean, I'd probably give you CD. It's not really technically drawn there yet, but I would totally give it to you. Yeah. How about 2 major arcs?
Major arcs would be RAC.
RAC works. RAD would work. DRC. You can't do that. Oh, that way. Yeah, DRC. DRC, right? So we're talking this direction. Yes. CAR would also work. RAC would also work. That's the same one. Yep.
CAR
CAD would also work.
We haven't put that one yet.
We have not.
That's a semicircle.
Are you?
No, because CDA is, I'm glad that happened though. CDA is a semicircle, but not CAD, right? Okay, so good segue. CDA is a semicircle. What else?
Can a major arc be bigger than a semicircle? Oh wait.
It has to be.
I put ADC.
CDR would be a major arc. RCD, you don't know that D is on the diameter, so that you can't assume. The only thing you could do for a semicircle is because this is the diameter, I could go that way, which is CRA or ARC, and then I could go this way, CDA, which is what we did, or ADC. But those are the only two that you know for sure are semicircles because that's a diameter. DAR, nope, because we don't know that this is we don't know that that's a diameter. It would have to be a straight line that passes through the center. Okay, how about an acute central angle? AOR, good, that's the only one. AOR, or ROA, obviously, but this one.
That looks more like 90 degrees to me.
It's definitely not 90 degrees. It's less than half, right?
No.
Yes, this would be 90.
Also, it's because I'm at an angle from the screen.
Okay, you also have it in front of your face. Okay, two congruent arcs. What are the only ones we know an exact measure of? Mars.
Well, D.
Semicircle.
Good. So CDA and CRA, the two semicircles, are the only ones we have an accurate measurement of. Those are both 180. Questions?
Wait, what about ARC?
ARC. Yeah, that's the same thing as CRA backwards. Yeah, those are the same ones. That works though.
Arc of the cover.
All right, example 2. Give the measure of each angle or arc, okay? So this time the information given to you, there's a couple things happening here. Obviously, we know 30 degrees, we know 50 degrees, but we also know that this is passing through the center. So that's a diameter. That gives you some information too, okay? So this, again, give the measure of the arc or the angle. So the arc of WX is this one. How do I find it? Okay, you're both right. So if this is 30, right, this is also 30. If this is 50, this is 50, so I can reverse those. And then this is a semicircle, so it adds up to 180. So if I did 180 minus the 30 and the 50, which is 80, this is 100 degrees. No. 100 degrees. Okay, the next one is WOT. But this is the angle. WOT, we already found, was 50 degrees.
That's a dope question.
Thank you.
No,
XYT is what?
210.
How do you get it?
180 plus 30.
Good. The 180, that's the semicircle, plus the 30, that's over here. And then, or you could subtract the 150 from the 360. Like all of it overlaps. And then the last one is YOT, which is YOT, which is 180. Good. It's a straight line or a straight angle.
How many homework questions are there?
I don't remember. Questions?
Yeah, under 10.